Hello, Professor Sargent here with you again to talk about multiplying and dividing radical expressions and simplifying our answers when possible. This first one, we've got two options. The first one, I don't particularly like. We could simplify that square root of 27. If I just focus on that for a moment, the largest perfect square that will go into 27 is 9. It goes in 3 times. So the product rule would tell me that I could split up the multiplication. Take the square root of the 9 and get 3 square root of 3. Then I would have to distribute the square root of 3 out here. When I do that distributing, parts that are outside of a square root, I'm going to put in front like a coefficient. So distributing square root of 3 to 3 square root of 3, putting the 3 outside in front. Same thing for this. The square root of 3 times square root of 3, there's a few ways we could view this, but we could go with the product rule in the other direction, put them together, and do the multiplication inside. Square root of 9 is 3. And I already had a 3 out there multiplied in front. So we're going to get 9 minus 3 square root of 3. That required putting something back together where I'd already done some breaking apart. So in option 2, I'm going to show what happens if we just distribute the square root of 3 to begin with. If I distribute the square root of 3 to the square root of 27 and the minus 3, I'll put the square root at the back, a coefficient in front. Working with the product rule in the other direction, put the 3 and the 27 together, multiplied together inside that first radical. And 3 times 7 is 81. Although that's larger, it should still be recognizable as a perfect square. Square root of 81 is 9. If you go back a bit, you should see that's the same answer I had in the end for option 1, but this approach is a little nicer. The distributive property is something we'll need quite a bit of. And in this next one, the shortcut I'm going to use FOIL, first, outer, inner, and last pairs. That's a shortcut for the distributive property when you have binomial times binomial. These aren't really polynomials, but we're acting similarly. So I would have 2 times 4 for the first. For the outers, 2 times the square root of 5. Since they're both positive, we're adding it. For the inners, both positive there as well. So 4 square root of 3. And for the last, square root of 3 times square root of 5. All we can do to simplify this is that multiplication there, It doesn't have a square root, so it's not going to be combined with anything. These two radicals, they are both square roots, but what's underneath the radicand is different. And if I put these back together, 3 times 5, we've got square root of 15. None of those can be simplified because there's no perfect square other than one that will go into 3 or 5 or 15. And we can't do any of the addition because they are not like radicals. This one we could view similarly. Square root of 6 times square root of 6 for the first. For the outers, minus square root of 6 times square root of 5. For the inners, plus square root of 5 times square root of 6. And for the last, since one's a subtraction and one's an addition, think of a positive and negative, we have square root of 5 times square root of 5. And similar to what we saw in example 1, we can put things back together, and if we have a perfect square underneath, then we get some cancellation. So putting square root of 6 times square root of 6 together as a single square root, 6 times 6, you've got 36, and it's square root of 6. Those square roots, since we have real numbers and we're multiplying the same thing, the squaring is canceling out the square root. In the middle, yes, we can find out that that's going to be square root of 30, which cannot be simplified, but we're adding the opposite of it here, and it is the same regardless of the order of the multiplication. So that's the middle two are going to cancel out, and we've got the square root of 5 multiplied to itself, i.e. squaring cancels it out. The second option would be to recognize that we're dealing with conjugates of each other. When you're multiplying two binomials that look almost exactly the same, but one of them has addition and the other has subtraction, there's a formula called the difference of squares formula. Our a in this one is square root of 6, and b is square root of 5. And as we saw in some earlier examples, the squaring of the square roots, since we have real numbers there, what's underneath the square roots are non-negative, then we'll get cancellation, and that's 6 minus 5 again. Just a bit quicker when we recognize that a plus b and a minus b are conjugates, and that we could use the difference of squares. Now, the order of the multiplication would not have mattered. It could have been a minus b, that quantity, times the parentheses a plus b. In number 4, we don't quite have conjugates. We've got the square root of 3 and the minus square root of 3, but different things multiplied to square root of 7. So for the first, multiplying the 7 and the 2, and that's times square root of 7 times itself. For the outers, 7 square root of 7 minus times negative square root of 3. Put the 7 in front, and 7 times 3 can be put together underneath one radical and multiplied to get 21. For the inners, same kind of thing. So we still have square root of 21 there. And then we've got minus square root of 3 squared, taking care of where the squaring cancels out the square roots. 14 times 7 there. 21. You cannot simplify the square root of 21 because the largest perfect square to go into 21 is 1. But we could add the negative 7 plus 2. So we're going to have minus 5 square root of 21. The square root of 3 and the squaring cancel, so we've got minus 3 there. 14 times 7 is 98, and I'm going to subtract the 3. So in the end, we wind up with 95 minus 5 square root of 21. You can't simplify the square root of 21 any further, and we cannot subtract 95 minus 5 because the 95 does not have a square root of 21 with it. Use FOIL again here, and we've got 6 times the square root of x squared, and we know that square root of x squared, we're going to get cancellation, so just 6x. Then we're going to have, for the outers, minus 3 square root of x. Let's see, yeah. Plus, for the inners, 2 times square root of 3 times square root of x. I'll put those together under a single radical and multiply. Finally, we've got, for the last, minus square root of 3. None of these are like radicals or like terms. We've got different things under each square roots. And this one doesn't have a square root, so we can't do any combination there. In number 6, we do have conjugates. So either FOIL or use the difference of squares formula. I'm going to use that second option. A is square root of 3x and B is 4. Squaring will cancel out the square root, and we're left with 3x minus 16. If we take the binomial a plus b and square it, i.e. multiply it by itself, you could FOIL this out. A times a is a squared. That's the first. The outers would be a times b. The inners would be b times a. And the last would be b times b is b squared. Well, AB and BA, the order of the multiplication doesn't matter, so those are in fact like terms that we can combine. That binomial squared is equal to, since we're adding these two like terms, one of each, a squared plus 2ab plus b squared. That's an example of a perfect square trinomial. Similarly, if it was subtraction and you did that FOILing out, it would look almost the same, except that in front of that middle term you'd have a minus 2ab. Feel free to check that out if you have never seen this before. So for example, if we were to square x minus 10, the quantity x minus 10, you can check this by using FOIL, but I'm going to use this formula. That would be A would be x, and B would be 10 in the second formula. Or you could even just use one formula, have A be x again in the first formula, and have B be negative 10 in that first formula. Either way. But going with the second formula here, so we'd have x squared minus 2 times x times 10 plus 10 squared. And we should not leave it this way. We know what 2 times 10 is. So x squared plus 20x, minus 20x. And we know that 10 squared is 100. And for this final one, we want to put this in lowest terms, show you what that means. Dividing by 2 is the same as multiplying by 1/2. Normally, I would not write the following step. My point is, we could distribute that 4 times 1/2, or 4 over 2 minus 4 squared of 5 over 2. Distribute that division by 2. We could not do that in the previous examples because we were dividing by binomials. Here it's a monomial, single term. And so we can reduce this to 2 minus 2 square root of 5. Looks a lot nicer than what we started with. That's all for now. I hope it's helped. And if it has, please like and subscribe to the channel.